The proposed research introduces SECRM-2D, a reinforcement learning (RL)-based autonomous driving controller that optimizes efficiency, comfort, and follows a fixed route while ensuring hard analytic safety constraints. Building on previous work in longitudinal car following, this controller incorporates lateral control actions for discretionary and mandatory lane changes. Safety is guaranteed by constraints derived from the criterion that the follower vehicle must have sufficient headway to avoid a crash if the leader brakes suddenly. Evaluations against several baselines in simulated scenarios confirm SECRM-2D's success in avoiding crashes, improving efficiency and comfort, and faithfully following the prescribed route. Furthermore, the study provides a theoretical understanding of the longitudinal steady-state behavior of a collection of SECRM-2D vehicles, demonstrating their ability to naturally form a steady-speed platoon. This advancement has significant implications for the development of safe and efficient autonomous vehicle systems. Advancing the application of reinforcement learning to train performant autonomous vehicle controllers, this work incorporates strong, explainable, and explicit safety constraints. Existing research on lane change topics is reviewed, highlighting limitations in addressing safety issues. The problem formulation involves training a controller for a single vehicle driving on a road with one or multiple lanes, acting in discrete time steps to set both continuous longitudinal acceleration and discrete lateral movement. The controlled vehicle obtains a fixed route from an independent routing module and performs discretionary and mandatory lane changes. Hard safety constraints, derived from the Vienna Convention on Road Traffic, ensure a minimum gap between the vehicle and its leader vehicle to prevent collisions. These constraints provide stronger safety guarantees compared to time-to-collision threshold-based criteria. The objective is to maximize a weighted combination of efficiency and comfort measures, subject to obeying safety constraints and following the prescribed route. Efficiency is measured by the vehicle's speed, while discomfort is measured by the vehicle's jerk. The task of maximizing efficiency is split into two subtasks: driving as closely as possible to the maximal safe speed within the current lane and carrying out lane changes to increase the maximal safe speed, subject to lane change safety constraints. Notation is introduced, including the ego vehicle, leader and follower vehicles, distances, and acceleration and deceleration rates. The requirements and notation are formalized to provide a solid foundation for the remainder of the paper. The longitudinal safety constraint is formulated based on the ego vehicle's reaction time, minimal stopped gap, and speed, ensuring a safe front gap in the event of an emergency stop by the leader. This constraint is derived using the laws of kinematics, resulting in equation 1. To avoid negative values, the defensive principle is adopted, assuming the ego vehicle's distance is less than or equal to the leader vehicle's distance. This leads to the ego vehicle's maximal safe speed at the next time step, given by equation 2. Similar expressions are derived for imaginary copies of the ego vehicle shifted one lane to the left or right, resulting in analogous expressions for maximal safe speeds. The safety constraints for the SECRM-2D model are formulated, including the acceleration safety constraint, where the ego vehicle's speed must satisfy equation 3, and the lane change safety constraints, which prohibit lane changes that would violate the safe gap inequality. The lane change safety constraints are elaborated for a left lane change, resulting in two conditions given by equation 4. The efficiency of a vehicle is measured by its average speed, which is bounded above by the road speed limit and the maximal safe speed. The target speeds are defined as the minimum of the maximal safe speed and the speed limit, given by equation 5. The inefficiency is measured by the difference between the current speed and the highest target speed. The comfort of the passengers is increased by minimizing the cumulative squared jerk over the controlled vehicle's trajectory, given by equation 6. The authors formalize the control problem as an optimization problem within a statewise constrained Markov decision process, SCMDP. Specifically, they define an SCMDP as a tuple consisting of the state space S, action space A, reward model R, S, A, S, transition model P, S, S, A, discount factor gamma, initial state distribution ρ, S, cost function C, and weights W. The agent's objective is to find a feasible policy that maximizes the cumulative discounted reward J, pi, equals E, tau tilde operator rho pi p underscore t equals 0 caret infinity gamma caret tr s underscore t a underscore t s underscore t plus 1. The state space includes features of the ego vehicle and other vehicles within a fixed scan radius, while the action space is a two-tuple, alpha, L, where alpha is an acceleration action and L is a lane change action. The reward function is a weighted sum of efficiency, comfort, route following, and discretionary lane changes. The state representation of the ego vehicle, as depicted in Fig. 3, includes the ego vehicle and surrounding vehicles. A discretionary lane-changing reward is formulated to encourage changing to a lane with a higher target speed, penalizing changes to a lane with a lower speed. This target speed maximization approach compactly encodes actions for various scenarios, including those with faster-moving leaders or no leaders on adjacent lanes. The immediate reward is boosted to compensate for the penalty accrued after the lane change. Mandatory lane changing, or route following, is achieved through a reward term that penalizes deviations from the fixed route. The combined optimization objective integrates these terms with weights for comfort, discretionary lane changing, and route following. This unified approach optimizes both discretionary and mandatory lane change decisions, a novel contribution in the application of deep reinforcement learning to autonomous driving. The Deep Deterministic Policy Gradient (DDPG) algorithm is employed to train the controller, where actions are encoded as pairs. The first component of the action pair corresponds to acceleration, while the second component corresponds to lane changes. To ensure safety, the acceleration action is constrained, and the lane change action is projected onto the available lane change space. The DDPG algorithm learns an optimal policy by iteratively updating the state action value function and the policy network. This process involves storing experiences in a replay buffer and updating the networks using mini-batch stochastic gradient descent. Target networks are utilized to enhance training stability. Figure 5 illustrates the setup, demonstrating how the reinforcement learning (RL) vehicle determines acceleration and lane changes based on the current traffic environment. The RL vehicle's decision-making process is informed by its learned policy, which is the result of the DDPG algorithm's optimization of the state action value function and policy network. This study evaluates the efficiency, comfort, and safety of an autonomous vehicle control algorithm in mixed traffic scenarios using deep deterministic policy gradients (DDPG). The algorithm optimizes vehicle control while enforcing constraints through action constraints rather than a safety term in the reward function. Two environments are used: a simple loop network and a real-world network based on the Queen Elizabeth Way (QEW) and Erin Mills Parkway, South Down Road interchange near Toronto, Canada. In both environments, the controlled vehicle learns to navigate through mixed traffic, optimizing efficiency, comfort, and discretionary lane changes while adhering to safety constraints. In the loop network, the controlled vehicle is trained with 25 human driver vehicles, each with randomly sampled speed limits, to learn how to bypass slower vehicles and achieve higher efficiency. In the QEW network, uncontrolled vehicles are generated at a fixed inflow rate, and the controlled vehicle has two possible routes: staying on the freeway or taking the off-ramp, with each route assigned randomly with equal probability. The DDPG model configuration consists of a discount factor of 0.99, a simulation time step of 0.1 seconds, and a replay buffer size of 1 million. The model features 3 layers of neural networks with 256 nodes in the hidden layers, and the actor and critic learning rates are set to 3e4. Target soft update rate is 0.005. And a batch size of 64 is used for gradient ascent. The model's activation functions are torch, ReLU for the hidden layers and torch, TANH for the last activation function. Training was run for 1,000 episodes for each of the 5 randomly sampled seeds, and the checkpoint achieving the highest cumulative reward across the 5 seeds was selected for evaluation. Figure 9 illustrates the convergence of efficiency and comfort rewards during training in the QEW network, displaying average values and 1 standard deviation across the 5 training runs. The geometry of the loop network plays a pivotal role in determining vehicle speed, as demonstrated in Fig. 6. This is evident from the analysis of the trained policy, where efficiency and comfort rewards converge during training, depicted in Fig. 9. In the long term, the longitudinal behavior of a collection of vehicles shows the formation of platoons at the same speed as the lead vehicle. A two-vehicle system, where the follower drives at its maximal safe speed and the leader maintains a constant speed, is also examined. Key equations, such as equation 10 and proposition 1, are critical for understanding the steady-state equilibrium of the system. These findings underscore the importance of loop network geometry in optimizing vehicle speeds and improving overall traffic flow. The paper analyzes the asymptotic stability of the equilibrium point in a system where a follower vehicle is trying to catch up to a leader vehicle. The update functions for the follower's velocity and gap are provided, and the Jacobian matrix is computed at the equilibrium point. The eigenvalues of the Jacobian are shown to have norm less than 1 when the parameter W is greater than 0, indicating asymptotic stability. In the case where W is equal to 0, the eigenvalues are complex and have norm 1, making it impossible to conclude whether the equilibrium point is stable or not. However, empirical results suggest that the behavior is similar to the W greater than 0 case. The paper then discusses how removing simplifying assumptions, such as bounded maximal acceleration in speed limits, affects the analysis. It is shown that with these assumptions removed, the follower may need an initial speedup period to catch up to the leader, and the analysis reduces to the previous case. The paper then moves on to discuss the implications of the analysis for SECRM-2D platoon formation. It is argued that a well-trained SECRM-2D model following a constant speed leader will have similar long-term equilibrium properties to the system analyzed, with the follower driving at speed W and maintaining a gap of WR plus DLDE, 2DLDE W2 plus epsilon. For a platoon of SECRM-2D vehicles following a fixed-speed leader, it is argued inductively that each vehicle will converge to the common platoon speed W, and the intervehicle gaps will be described by the previously obtained formulas. Empirical tests confirm this expectation. Finally, the paper notes that if vehicle velocities are constrained by a speed limit, it may not be possible for a follower vehicle to catch up to its leader, and a collection of SECRM-2D vehicles may form into several platoons. The paper concludes by outlining the baselines used to evaluate the performance of SECRM-2D in subsequent experiments. The authors evaluate the SECRM-2D controller in a loop network under 3 scenarios: normal driving, congested traffic, and emergency braking. Performance is compared to 3 baselines: IDM plus mobile, GIPS plus greedy, and PP-based reinforcement learning. Table 2 presents the results, showing SECRM-2D outperforms the other methods in terms of average speed, jerk, and crash rate across all scenarios. SECRM-2D achieves the highest average speed and lowest jerk, indicating both efficiency and comfort. In contrast, GIPS plus greedy and IDM exhibit either higher jerk or lower average speed, while PP-based RL has a higher crash rate. The dynamic target gap of SECRM-2D adapts to the current driving situation, ensuring safety and efficiency. In the congested traffic scenario, the differences between methods are minimal due to the high number of vehicles. The emergency braking scenario demonstrates SECRM-2D's ability to generalize well and maintain safety under unexpected events. The GIPS model is extended with a lane-changing model, resulting in GIPS plus greedy, which prioritizes efficiency over comfort. The authors conjecture that SECRM-2D converges to GIPS plus greedy as the comfort weight Chi-Conf approaches 0, suggesting SECRM-2D can be seen as a more comfortable version of GIPS plus greedy. This highlights SECRM-2D's ability to balance efficiency and comfort, making it a promising approach for autonomous vehicle control. The SECRM-2D vehicle's performance is evaluated in various scenarios within the QEW network, including bypassing, emergency braking, and merging tasks. In the bypassing scenario, the controlled vehicle navigates through a zigzag fleet of human-driven vehicles with a lower speed limit, demonstrating its ability to conduct safe, efficient, and comfortable lane changes. In the emergency braking scenario, the controlled vehicle must brake to avoid collisions when encountering sudden deceleration from leading human-driven vehicles. The merging scenario tests the vehicle's capacity to merge into the main line from an on-ramp under challenging conditions. The results of these experiments are analyzed and compared to two baseline models, IDM plus mobile and GIPS plus greedy. Over the course of training, the SECRM-2D agent improves its efficiency, comfort, and routing objectives while reducing the route miss rate. Unlike other RL baselines, SECRM-2D achieves a zero crash rate in all scenarios, particularly in emergency braking, thanks to accurate estimates of reaction times and braking rates of surrounding vehicles. The SECRM-2D model, a safe, efficient, and comfortable reinforcement learning-based driving model with lane-changing capabilities, was tested in various scenarios to evaluate its performance. In the bypassing scenario, SECRM-2D generalizes well, achieving higher average speed, lower jerk, and better safety and route following performance compared to rule-based and RLBASED controllers. As the headway decreases, the model's performance improves, demonstrating its adaptability in different traffic conditions. In the emergency braking scenario, SECRM-2D maintains low average jerk and zero crash rate, showcasing its superior safety performance. The merging scenario results, obtained without retraining the controller, illustrate the model's ability to generalize to different route-following scenarios successfully. The efficiency and comfort of the model depend on the reaction times of the controlled and human driver vehicles in the challenging bypassing scenario, with lower reaction times enabling higher efficiency control. The SECRM-2D controller successfully avoids crashes in both training and testing, outperforming several representative previously published RLAV controllers. In the realm of microscopic traffic simulation, car-following models play a vital role in replicating real-world traffic conditions. However, existing models often fall short in capturing the complexities of vehicle behavior, particularly when it comes to lane changes. To address this limitation, we propose the SECRM-2D model, which integrates both mandatory and discretionary lane changes using deep reinforcement learning. By leveraging a two-dimensional state space, SECRM-2D can accurately capture the dynamics between vehicle speed and intervehicle gaps, providing a more realistic representation of traffic conditions. The SECRM-2D model's development is rooted in the concept of deep reinforcement learning, allowing for the optimization of vehicle control strategies through trial and error. We evaluate the model's performance using the Sumo microscopic traffic simulator and compare it to other state-of-the-art models. Our analysis reveals that SECRM-2D achieves stable and efficient vehicle spacing, even when considering both mandatory and discretionary lane changes. We further investigate the long-term equilibrium of a platoon of SECRM-2D vehicles moving at constant speed, deriving a precise expression for intervehicle gaps in terms of speed and vehicle configuration. This analysis demonstrates the model's ability to maintain stable and efficient vehicle spacing. Additionally, we verify the asymptotic stability of the follower with a constant speed leader system, ensuring that the eigenvalues of the Jacobian matrix at the equilibrium point satisfy lambda plus or minus less than 1 whenever W greater than 0. The SECRM-2D model offers a significant advancement in the field of car-following models, providing a more realistic and efficient approach to microscopic traffic simulation. Its potential applications include enhancing the realism of traffic simulations and improving the efficiency and safety of automated vehicle control strategies. Future research directions include incorporating additional factors like weather conditions and pedestrian behavior into the model, further refining its ability to replicate real-world traffic conditions. Case B, where W2-2WDR-D2R2 less than 0 is considered. In this scenario, the eigenvalues lambda plus or minus are complex conjugates. To establish stability, it suffices to show that either of the eigenvalues has a norm less than 1, since complex conjugation preserves norms. The squared norm of lambda plus is calculated as W2 plus D2R2 plus 2WDR minus W2, 2W plus Dr. 2, which simplifies to D2R2 plus 2WDR, 2W plus Dr. 2. To demonstrate that lambda plus 2 less than 1, it is equivalent to show that D2R2 plus 2WDR less than 2W plus Dr. 2. Expanding the square and rearranging. This condition is equivalent to 0 less than 4w2 plus 2wdr, which holds whenever w greater than 0. Consequently, lambda plus or minus, less than 1, as desired, implying stability in this case. This result has significant implications for the overall analysis, as it demonstrates the robustness of the proposed approach in handling complex eigenvalues.